How tunnel boring machines dig through solid rock. Imagine a machine nearly as tall as a building, buried underground, pushing its way through solid rock. Its giant cutting wheel spins forward while thousands of tons of force press against the mountain. But here is the mystery. How can a machine this enormous actually eat through solid rock without destroying the tunnel around it? The answer is one of the most impressive engineering systems ever built. Let's find out. The impossible job. Deep underground, engineers may need to create a tunnel through rock that has been undisturbed for thousands or even millions of years. Digging it with ordinary excavators isn't practical. The machine would need to work underground, remove enormous amounts of broken rock, keep the tunnel aligned, and create a safe passage behind itself. And there is another problem. Rock is not always the same. Some layers are relatively soft. Others can be extremely hard. So engineers cannot simply build one giant drill and expect it to work everywhere. This is where the tunnel boring machine, or TBM, enters the story. Picture a massive steel cylinder stretching far behind a rotating cutting wheel. At the front is the part everyone notices. The enormous circular cutter head. But surprisingly, the cutter head isn't designed to simply drill through rock like a giant metal pencil. It works in a completely different way. How the rock actually breaks. Look closely at the front of a hard rock TBM. You will find dozens of circular cutting tools called disc cutters. Each one is made to withstand tremendous forces. Now imagine pressing a small metal wheel against a block of hard material. Instead of simply scraping the surface, pressure concentrates around the contact point. The rock begins to crack. And here's the clever part. The cutter head doesn't work alone. Behind it is an entire system designed to collect the broken rock and carry it away. Otherwise, the machine would quickly bury itself in its own debris. The rock has to go somewhere. Imagine breaking thousands of pieces of rock every minute. Where would all of it go? This is one of the biggest challenges of underground excavation. As the cutter head rotates, broken material falls toward the lower part of the machine. From there, the material can be collected and transported using systems such as a conveyor. The conveyor continuously carries the excavated rock toward the rear of the TBM. Eventually, the material can be transferred out of the tunnel. Think of it like a gigantic underground factory. Leaves. And the machine keeps moving. But now engineers face another problem. The machine has to move forward. A rotating cutter head cannot push a tunnel boring machine through rock by itself. So what pushes the machine? The hidden muscle. Now let's look behind the cutter head. Inside the TBM are powerful hydraulic systems. These systems operate cylinders that can push the machine forward with enormous force. But the machine needs something to push against. This is where the tunnel structure becomes important. Depending on the TBM design and ground conditions, the machine uses different methods to create forward movement and support. In hard rock tunneling, the machine advances gradually while the excavated tunnel is supported using methods suited to the surrounding rock. Some TBMs work with rock support systems that may include rock bolts, sprayed concrete, steel supports, or other reinforcement. In other tunnel designs, precast concrete segments are installed behind the machine. The exact system depends on the geology and the type of TBM being used. The machine must know where to go. Now imagine driving a giant machine underground where you cannot see the road ahead. A tiny mistake in direction could eventually move the tunnel away from its planned path. So how does a TBM stay accurate? Engineers use sophisticated guidance systems. Lasers, sensors, surveying equipment, and computerized monitoring can help track the machine's position and orientation. The TBM can measure where its front section is pointing and compare that position with the planned tunnel route. If correction is needed, hydraulic systems can adjust the machine's movement. Think of it like steering a gigantic vehicle through a mountain while following an invisible line. But even staying on course isn't enough. The rock around the tunnel can move. Pressure can change. Water can appear. And different layers can behave completely differently. So the machine must constantly respond to its environment. The tiny details that protect the tunnel. Here's something many people never think about. The tunnel is not finished simply because the TBM has passed through. Engineers must create a stable tunnel behind the machine. In many modern tunneling systems, precast concrete segments are installed to form a strong ring. Imagine several huge curved concrete pieces coming together like sections of a giant underground puzzle. Once assembled, they create a continuous lining. In some systems, grout is injected into the space outside the lining. This can help fill gaps and provide support around the installed tunnel lining. And notice something unusual. The machine is moving forward while construction is happening behind it. Excavation, material removal, steering, support, monitoring. All of these operations have to work together. That's what makes a TBM more than a drill. It's essentially a moving underground construction factory. But what about water and different ground? Now comes another major challenge. Not every tunnel passes through dry, predictable rock. Some routes encounter groundwater. Others pass through softer soils. This is where different types of TBMs become important. For softer ground, engineers may use machines such as earth pressure balance machines, commonly called EPB TBMs. Another type is the slurry TBM, which uses a pressurized slurry system to help manage the excavated material and ground pressure. These machines work differently from traditional hard rock TBMs. Why? Because the engineering problem is different. In hard rock, breaking the rock efficiently is a major challenge. In soft or water-bearing ground, maintaining stability and controlling pressure can become much more important. So when you see a TBM described as a giant underground drill, remember, that description is only part of the story. Everything works together. Now let's step back and watch the entire process. The cutter head rotates. Disc cutters press against the rock. The rock fractures. Broken material is collected. Conveyors or other transport systems move it away. Hydraulic systems push the machine forward. Guidance systems keep it aligned. Support systems stabilize the newly created tunnel. And behind the machine, the tunnel gradually becomes a finished underground passage. All of this happens while the machine advances through a world humans normally cannot reach. And here's the most impressive part. The TBM isn't simply overcoming the rock with brute force. It is using controlled force, mechanical design, monitoring, and precise timing. Every part has a job. The cutter head breaks the rock. The hydraulic system moves the machine. The transport system removes the material. The guidance system controls direction. And the support system protects the tunnel. A tunnel boring machine may look like one enormous machine. But inside it is an entire collection of engineering systems working as one. And that is the real lesson. The biggest engineering achievements aren't powered by one clever idea. They happen when hundreds of smaller ideas work together perfectly. What looks like an impossible hole through solid rock is actually a carefully controlled process of physics, machinery, and human engineering. And beneath the modern world, machines like these are quietly changing the way we build it. Disclaimer: this video uses AI-generated visual illustrations to explain real engineering concepts. The visuals are artistic representations intended for educational purposes.